So we want to talk about the fuel performance properties that are specific to specific combustion devices. And so a very important one, particularly in this country, also in China, is gasoline engines for cars. And in those engines, the way it operates is you premix the fuel in the air cold, and then you compress them, and then you light it with a spark. And you need to make a good premixing, to make the premixing easy, you want a fuel that evaporates at relatively low temperature, so that when you mix the fuel in the air, you're not trying to mix a liquid in a gas, you're mixing a gas in a gas. And so that's one reason you want gasoline to be low boiling. Also, you want the ignition delay to be long. You don't want the fuel-air mixture to spontaneously combust. If it can spontaneously combust too easily, it actually could be a safety hazard. And also, when you run the engine, the way it works is you want to actually use the flame made by the spark to burn all of the fuel in the air. You don't want any of the fuel in the air to spontaneously combust, because when that happens, it could actually make a detonation wave, or and it's called a knock, which might actually even damage the engine, because you have a pre-mixture, stoichiometric mixture of fuel and air. If you do spontaneously ignite that mixture, you can make an explosion. In fact, that's how they make the explosions that are in the movies, the action movies. You see all these explosions. It's gasoline mixed with air. So you really don't want that to happen in your engine at 3,000 times per minute. The engine's not going to last very long if it has explosions in it. So you want to have a nice smooth burning at a finite rate by the flame front. So that means you want the auto ignition delay to be very, very long. So you never want it to auto ignite. You only want it to ignite because the spark forces it to ignite. And the higher you can make that delay, the higher compression ratio you can operate in the engine. And these engines almost always operate at knock limited, so they push all the way up until the engine just barely starts to knock. And if you could make the fuel better so it didn't auto-ignite, then you could use a higher compression ratio, which means you get more power out of the engine and also have a higher fuel efficiency. So that's the crucial thing. And in fact, for things like race cars, where it's very important to get the very most amount of power and fuel efficiency out of the vehicle, then they try to make the very best fuel they can possibly find. Race car fuel is like just will not auto-ignite at all, because they want to be able to run at the very highest compression ratios. The measurement of that is called octane number, sometimes called RON or MON, and those are the way we measure the auto ignition delay relevant to an auto engine. You also need a sufficient flame speed, and you also need resistance to extinction so that all the fuel will actually burn up. You don't want to have fuel that you put in the cylinder that doesn't burn, because first of all, you're wasting fuel. And second of all, that unburned fuel is going to come out in the exhaust, and then you have to trust your exhaust control system to eat it up. And if not, it's going to go out into the environment, and then it's going to cause smog. For diesel and jet engines, the generally easy ignition is preferred. Like in a diesel engine, you don't have a spark, so you have to get the fuel to somehow light. So you need to have it be able to ignite. You want the fuel to have, it's going to be, you compress the air first so it's hot, and you inject liquid fuel into hot air, very hot air. And so you want, at that temperature, you want the fuel droplets to all evaporate before they can reach the other side of the cylinder. Otherwise, they'll hit the cold wall, and there'll just be liquid film on the wall, and they won't burn. So you have to have, it has to be volatile enough, low boiling enough, that the liquid will actually evaporate during that transit time from the fuel injector towards the wall. And you want the fuel to have resistance to soot formation, because you expect that you're going to operate this engine where there's going to be a lot of regions that are fuel rich, because you're injecting, you have unmixed fuel going into air, and it's not well mixed. So you're definitely going to have regions that are fuel rich. And so you're going to have pyrolysis chemistry there, and potentially you could have soot formation. And that would be really bad if you make a lot of soot, because then you'll emit soot particulates. You might kill people from breathing in the particulates. And so certain fuels have more resistance to soot formation than others. And so that's kind of a quality you want. However, I would say that this is not that well understood and not that well regulated, because it's not that well understood. But it's observed that some batches of diesel fuel make more soot than other batches, and sometimes they make some regulations to try to figure that out. Okay, fuel rich versus fuel lean. What do we expect? if we have a fuel-rich system, well, a fuel-lean system, you expect that when you run to equilibrium, it's all going to be CO2, right? You have a lot of oxygen. All the carbon atoms will burn out to CO2. If it's fuel-rich, if you consume all the O2, you're still going to have some CO or hydrogen left over because there's just not enough oxygen atoms there. But it turns out that if the O to C ratio is greater than 1 to 1, you don't really expect to make soot, at least not at equilibrium. Because what will happen is that all the carbon atoms will bind an oxygen atom because CO is much more stable than everything else. So the carbon really wants to grab the O. So if you get to equilibrium, it's going to be CO. And then the hydrogens will be left without a partner, without the oxygen, because they can't bind the oxygen as hard as the carbon does. If the O to C ratio is less than 1 to 1, then you'll burn up all the O atoms, basically all to make CO, and you'll still have some carbon atoms left over. And then you'd expect to make a lot of soot because you have carbon atoms left over. You're basically doing pyrolysis there. You burned some of the carbon to make CO, got some heat release, and that heat is going to then pyrolyze all the rest of the fuel. And this is very prone to making soot. Also, the temperature will be different. As you get more and more fuel rich, the temperature will get lower and lower and lower because you have less oxygen or more heat capacity of this extra fuel that you're carrying around. So that's about it. All right, so air pollution is a major constraint on all the combustion devices. So we have pollutants that are hydrocarbons that go into the atmosphere. Some of these actually come from fuel evaporation, like in the gas station, or leaks in the refineries and stuff. And so you get some fuel evaporation there. That's actually a pretty significant amount. And then you can also have some that goes through the engine and comes out the tailpipe. It doesn't burn. What happens particularly is that if you have a crevice in your piston around the edge of the piston, that little crevice region is colder than the rest, and a lot of times it won't burn in there. So you have a little bit of fuel that gets jammed down into the crevice by the pressure as you compress it. That fuel never burns, and then when you open the valve, it gets emitted into the tailpipe. Some of it burns up in the exhaust system. Sometimes the emission control system can catch it, but some of it will leak all the way through. The carbon monoxide emissions, as I showed you, the equilibrium concentration of carbon monoxide is still pretty high. Even if you run a stoichiometric flame all the way to completion, you'll still have some CO left over. That CO is going to go out. It's a toxic gas. You know, if you run a car in a garage, you might not live, right? It's pretty dangerous. Fortunately, it's relatively easy to do oxidation catalysts to burn up the CO. So at the high temperature, at the end of the combustion, you have some CO there at equilibrium. However, as you cool it, the equilibrium favors making the CO into CO2. So as it's cooled into the exhaust system, then the equilibrium is favoring burning up the CO to go to CO2. And if you have a catalyst to help that happen, then you'll burn the CO up to CO2. And there's both diesels and spark ignition engines in America, and I think in probably most of the countries, now have oxidation catalysts to burn up the CO. NOx is made very much by motor vehicles, but also by stationary burners. And this turns out to be very important in photochemical smog. We'll talk more about that in a second. Sulfur oxides are primarily come nowadays from coal. And in the United States, the coal power plants are required to have a scrubber to try to capture the sulfur dioxide to reduce the sulfur emissions. I'm not sure. I think in China they just started to do this. Probably Europe probably has the scrubber similar to the US. And that's a very bad pollutant. It makes particulates in the atmosphere. It's bad because of pulmonary disease, and it makes acid rain, which can kill the lakes. And in the U.S., most of the rain in the eastern United States is acidic because of the sulfur, even despite the fact that we have the controls. And also, the NOx also can make nitric acid, which is also acidic. And then the particulates, diesel engines and coal power plants are famous sources of particulates. I think actually all kinds of combustion makes a little bit of particulates. And it's more and more recognized how very bad they are for human health. The particulates are also formed secondarily from the smog chemistry. And then CO2, everything, the whole idea of combustion is to make CO2. And so, of course, they all emit CO2. And also things like deforestation, changes in land use also have big effects in CO2. All right, so this is an acid range. This is 2001. The rainwater in the US is typically a pH 4.5, which is pretty strong acid. It's like vinegar. So that's not too good. And the NOx, current concern a lot about NOx is about the photochemical smog reactions, which I'll talk about in a second. The humans are, as we said before, they're dumping a ton of CO2 into the atmosphere, all of us. And it's driving the CO2 level in the atmosphere much higher than normal. And trying to figure out how to stop it is really hard because you can see this was like the normal level of CO2 and then it started going up. This is like the integral, this is the rate, emissions per year. And the emissions per year have just gone up, pretty much since the Industrial Revolution started. This is the COP21 pledges. And basically the pledge, this is, if you didn't have any new change in policy, this is the expectation, is the amount of gigatons per year emissions. And it would just keep going up and up and up and gradually maybe flatten out as efficiency things started to take over. With the pledges of the COP21 treaty, the countries basically pledged to stabilize the CO2 emission levels about where they are now and then gradually reduce them. So the emissions per year of the CO2 would gradually tail off. However, what matters to the atmosphere is the integral of how much CO2 is dumped in, because once you put the CO2 in the atmosphere, it basically stays there. And so if you wanted to actually stabilize the climate, you'd have to bring the CO2 emissions down all the way down close to zero by the end of the century. And so that's really a challenge to figure out how to do that. I think even to achieve this is going to be reasonably hard. And it requires a lot of help by the technology, by the engineers. And to get down towards anywhere down here is a really big challenge. But that's sort of where we have to go eventually, or else we've got to build a heck of a lot of dikes because all the coastal cities will be underwater. And the agricultural areas are all going to move around depending as the temperature changes. Historically, there's been a near perfect correlation of the amount of CO2 in the atmosphere and the global temperature. So this is for the last 400,000 years. These are from ice cores in Greenland and Antarctica. And they infer the temperature from an isotope effect on oxygen, which I don't understand, but it's something that turns out to correlate with the temperature. And so here's the variance in the temperature. It actually varies a lot because we had ice ages, right? So every time there's an ice age, the temperature is way low. And then when there's enough CO2, the temperature goes back up. And then as the CO2 gets absorbed, then it goes back down and so on. So that's what's been happening during this recent geological epoch because we've had a lot of ice ages. And so currently we're up at a hot point because we're out of the ice age. And now we're going to make it hotter and hotter, a couple more degrees hotter. So we're up here somewhere. Now, on the geological timescale, the variation that we're imposing as humans is not that big. The Earth has been hotter before. So it's not like the Earth is going to cease to exist because of the climate effect. However, species have gone extinct before, and we might be one of them. So from the point of view of us, it could be a really big deal. From the point of view of the Earth, eventually there'll be some geological process. The carbon will go somewhere else. Eventually, it'll all work out. Some new species will evolve that can tolerate higher temperatures or something. So it's not like it's going to be forever, but it could be bad getting there. And this is a really important thing for you to know about, is that there's a big controversy right now about what's really going to happen. So how much fossil fuel is really going to get burned is the main question. And the Financial Times wrote a nice article about this where they said, the climate scientists have calculated that they think we can put so many gigatons of carbon, CO2 into the atmosphere before the climate's going to be completely disrupted. And exactly what this number X is subject to some technical controversy with some error bar. And I surely don't know. But it's some number. And most of the world's governments have decided that they agree with that number. So they basically that's what the COP21 was all about, was reaching an agreement, sort of what's the real situation, how much CO2 can we really emit before we'll have a big problem. Now, the fuel companies, they issue numbers all the time, which are their fossil fuel reserves. How many gigatons of carbon do they own under the ground somewhere? So they've bought the rights to own so much amount of oil, so much amount of coal, so much amount of natural gas. And so they have identified a lot. And they like to make that number really big, because then it makes you want to buy stock in the company, because they own a whole lot of stuff. All right? So they have a number. But the curious thing is that this number y is significantly bigger than this number x. So the fossil fuel companies own a lot of fossil fuels, but the governments of the world have agreed that we're only allowed to burn this much. So that means there's y minus x of the fossil fuels that we know about, that the companies own, probably, I don't know, maybe can't get burned. So the companies own them, they're proud they own them, but they may have to leave them under the earth forever. So either we're going to burn the y, and therefore the stock prices of those companies are correct, because they're going to make a lot of money selling all that fuel to everybody. Or, but we do that, we're going to wreck the climate. Or a lot of investors who've buying the stock have owned this fossil carbon that's never going to be burned, is worth nothing. So it looks like somebody is going to lose a lot of money. So either the stockholders are going to lose a lot of money, or the people who own beachfront property are going to lose a lot of money, because they're going to be underwater, right, if all the fossil fuels burned. So somebody's going to lose a lot of money here. But right now, you want to buy a house on the beach. It's still really expensive. And if you want to buy stock in like Exxon or Saudi Aramco, they're about to sell their stock. You know, that's very expensive too. So people are spending money to buy stuff for the future that's not really worth. They can't both be right, right? And I'm concerned about this. I'm getting close to retirement age, and I'm thinking like, oh, I wonder how much of my pension is invested in stuff that can never actually work out. That's a little bit of an alarming thought. And I would say that this is another example of my general observation of life, is that humans are inconsistent. That's how you can tell somebody's a human. If they're a robot, they'll be consistent. If they're a human, they're inconsistent. So, you know, we all want to maintain the climate, but we also want to burn fuel because we like to travel and we like to use electricity. And we're willing to pay money to own stuff to be used in the future. So that's the way humans are. And the fact that those things are incompatible and they can't both be right doesn't stop us. All right? So I drove a car to get here, and I own stock in Exxon. And so, wait a minute, something's wrong, you know. I'd like to go to the beach. I'd like to have a beach house if I could, you know. So anyway, something's not quite right. All right, that's the long-term problem. The shorter-term problem is that a lot of people are being killed by combustion-related particulates. And anyone who's ever in an environment where there's a lot of particulates in the air knows it's bad, right? People put cloths over their mouths to try not to breathe it. If they have some more money, they pay for fancy systems to clean the air in their apartments or whatever. Everybody knows it's bad. So presumably there'll be political pressure on the governments to try to change things to somehow get that under control in regions that have high particulate emissions. There's really strong epidemiological evidence that particulate levels correlate with mortality. I think the causal relation of how the particulates kill people is not that well understood. But the fact that it does is not in debate. There's two big sources of particulates, actually three. In some areas of the world, it's actually dust. So they live near deserts. The dust storm comes in, you get a lot of particulates. In a lot of places, it's particulates coming directly from combustion of biofuels or biomass. And it can be, if you live in Singapore, you get a lot of particulates coming from Indonesia when the farmers they do like slash and burn agriculture, and they burn all the biomass. That's really horrible. It makes a lot of particulates. It causes a lot of trouble in Singapore. In a lot of places, it's fossil fuels making a lot of particulates. And then another big fraction is actually secondary particulates formed from smog chemistry. The hydrocarbon vapors that are emitted react with the NOx and make smog. The smog partially oxidizes them, they condense, and they actually make particulates which are just as bad for your health, I think, as the other particulates. Here's the epidemiology. So this is the correlation between the fine particle concentration in the air and the number of people who died that day. And you can see it's pretty much a straight line. So if you have 10% more particulates, or twice as many particulates in the air someday, you've increased your probability of death by like 15% that day. And this is just all they did is they went to the morgue, the mortality, the people give death certificates. And they said how many death certificates you did each day. And then they plotted from the weather station what's the particulate in the atmosphere today. And it's like a perfect correlation. So I guess that this means probably is if you're maybe close to death, you're sick, and then you get a bad particulate day, boom, you're done. This one is more chronic. This is China did an experiment unintentionally where they had a building code that was different north of the River Huai than it was south back maybe 30 years ago, 40 years ago. I'm not sure exactly when they made this rule. And they said, when you build all the new houses here, we'll put in heaters. And they used to supply a solid fuel to burn in the heaters. And that's what most people use to heat buildings. South of the river, they said, it's warm down there. No heaters. Too bad for you guys. So south of the river, like if you're like Shanghai, people used to wear a lot of clothes in the winter, many, many layers of clothes because they had no heat. So it was cold. People used to get frostbite, chilblains, all kinds of stuff, problems related to coldness. Any of you guys from South China? I don't know. Yeah, so if you know this experience, what I'm talking about? Maybe you're
I'm from south side.
Way far south.
Yeah.
So it's never cold anyway.
No, I'm close to Shanghai.
So do you wear all the clothing? A lot of clothing in the winter? Yeah, okay, right? So that's I saw a picture of, okay. We have heaters, the better, yeah. So people in the south, I saw pictures of the kids. They're like this because the parents put 15 layers of clothes on them. They can't move their arms up and down because they're wearing so many clothes. Okay? So they were complaining, but actually they were the lucky ones because the ones in the north have 5 years less life expectancy north of the river because they're breathing the particulates every winter from all the burners. And so, I mean, this is a very good scientific experiment, right? There's a lot of people who live up here, and a lot of people live down here too. So you have a very good statistical sample. This is maybe one of the best epidemiology experiments ever conducted for the sense of being a perfectly firm conclusion. It's kind of scary. 5 years is a lot, right? It's like, I don't know, 1/14 of your life or something. It's a very significant fraction of your life is being lost because of poor air quality. And I just emphasize, this is data from USA, this is data from China. I mean, people are the same everywhere, and breathing particulates is bad wherever you are. All right, so let's talk about pollutants. First, we're going to talk about NOx. So in the atmosphere, combustion devices emit NO. NO is formed. We'll talk more about how that happens. The NO comes out of the tailpipes, and it goes into the atmosphere. And in the atmosphere, there's HO2, is a pretty common species in the atmosphere. It's actually formed from hydrocarbon oxidation. We'll talk about that in a second. The NO converts the HO2 into OH. OH is a radical which is so reactive that even at room temperature, it can react fast. And it quickly attacks a hydrocarbon and makes it into a hydrocarbon radical, which then oxidizes, reacts with the oxygen. This reaction converts the NO into NO2. The NO2 absorbs the sunlight and goes back to NO. So you have a cycle where the NO is going back and forth, and the rate of formation of the OH is proportional to the amount of NOx, the total amount of NO and NO2 you have in your system. That's given the rate of formation of OH. The OH is 100% basically consumed by reacting with the hydrocarbons if you're in a polluted atmosphere. And so if you're in a city, there's a lot of hydrocarbons, the OH reacts with the hydrocarbons, and so then the number of hydrocarbons being oxidized, or the oxidation rate, is just proportional to the amount of NO. So oxidation rate just linearly proportional to NO. As a side note, this, as a co-product, these O atoms react with O2 to make ozone. Ozone is also a pulmonary irritant. So in places with high NO, you're oxidizing your hydrocarbons into oxidized stuff, which turns out, some of that oxidized stuff turns into particulates, which are bad to breathe. And you're also making ozone. And so places that have high particulates from secondary aerosols also have high ozone levels. And the sick people who are breathing them, they're dead. Okay? So that's what's going on here. Now, so this is the main reason we don't want to emit the NO, because this is a very serious health problem in the cities. And actually, in some areas, not just the cities. So actually, in whole northeastern US, in a big part of northeastern China, there's so much NO emitted from all the cities upwind and it all flows on top of them, and they all are breathing this bad air. And it's not just right in the city, it's like a lot of place, everywhere. And this is catalytic. It takes actually, the NOx doesn't go away. So it's like, you can blow along in the wind and still come and be bad. Okay, the NOx chemistry affects combustion chemistry in several different ways, but I would say that this is not really well understood. So there's a lot of empirical evidence that if you put some NOx into a combustor, into an engine, the behavior changes. But it's not huge. It's like you see a change, but it's not gigantic. And I would say the chemical mechanism of how exactly this works is not completely worked out. So this is like a current research topic that people are trying to figure out about this, what's going on. In combustion, there's several different ways that the nitrogen that's in the air is being converted into NO. And this is the main way that we make the NOx and make the NO. And this is discussed below, and that's our main topic about how you make the NO. And then there's a whole bunch of different reactions and different strategies that you can use to try to reduce the NOx coming out of the combustor, or to try to get rid of the NOx in your tailpipe in your emission control system. And I'm not really an expert on this, and there's a lot of different ideas about how to do this, so we're not going to talk about it too much. All right. So how is the NOx formed in combustion? It turns out there's at least 4 different pathways that are comparably important. So this makes it very confusing, because it's not just like one pathway, there's completely different ways. This one at the bottom has been known for a really long time, and a very smart guy named Zeldovich figured this out. And he figured out that if you make O atoms, they actually can directly react with the nitrogen and make NO plus N. This reaction is incredibly endothermic, because an O atom is a lot more stable than an N atom. And so, or you have to break a triple bond here to make this happen, right? So this is really endothermic. But in combustion, you make O atoms from the combustion reaction, right? H plus O2 makes O atoms. So you have a lot of O atoms just after the combustion. And you have a lot of nitrogen, because that's what we have in the air. So you have plenty of reactants. And so even though the rate coefficient is slow, this actually is pretty significant. And if you're in a stoichiometric flame or an a flame that's stoichiometric flame, so your adiabatic flame temperature, then this rate is actually the dominant source. It's the main source of NO. And so for a long time, this was known for a long time, and then people thought, okay, the main thing we can do to try to reduce the NO is to try to lower the temperature. And so there's a whole kind of strategies about how you can try to make sure that the peak temperature doesn't get too high. These other 3 are way more complicated. Well, yeah, they're way more complicated. So you'd expect, if you have some nitrogen inside your fuel, chemically bound, then maybe somehow that can react to make NO. I would say that's still true, mostly not known very well. Maybe it makes HCN and the HCN burns, I don't know. So this is something that people observe. If I put a fuel in that has more nitrogen, I get more NOx. And it's a pretty significant effect. But a lot of fuels don't have very much nitrogen, so it's not a gigantic thing, usually. But it's the same order of magnitude as these other paths. In 1970, Fenimore wrote a paper where he observed NO happening right in the primary reaction zone in a flame before you get into the exhaust zone. And he figured that this should be some kind of hydrocarbon radical actually reacting with the N2. And he suggested that this was the reaction. CH plus N2 goes to HCN plus N. And that would be a way of making N atoms, which would then do the same kind of reaction to make NO. And the HCN also might burn and make some NO. We'll talk more about this. This was proposed in 1970. For sure, some NO is formed immediately, separately from this mechanism. But exactly how it happens has been kind of controversial. And then very recently, another path was discovered where you have a lot of H atoms formed in combustion, and you have a lot of nitrogen. So you actually have an equilibrium that these guys exist with the species N and H, which is a really weirdo radical species, very short-lived. However, so you have an equilibrium concentration of this, and where you have a lot of H atoms, often you have a lot of O atoms, because you're making the O atoms by H plus O2. So if you have O atoms also present where this is present, you'll get some of this reaction. And this reaction is actually pretty fast, and it makes NO plus NH. And Tony Dean proposed this reaction, and then later some people did experiments and verified this is indeed true. And at very low temperature flames, this often is the dominant one, source of the NO. All right, so here's your quiz question. So the thermal NOx production, the main reaction there is extremely endothermic. So it has a gigantic EA, because remember EA is always bigger than delta H of the reaction. And so it's extremely sensitive to temperature. Now, in many practical combustion situations, both in gasoline engines and also in diffusion flames, the flame front's happening right at the stoichiometric mixture, so it has the highest possible temperature it could have. And so therefore, you get the highest possible rate of this reaction, which is really bad, and you make a lot of NO. So I want to know, what could you do if you're locked to have to do your combustion at stoichiometric? What could you do to try to reduce that peak temperature and then therefore reduce the NO formation rate? So talk to your partner, see if you can figure out an idea of what you could do. Nitrogen from oxygen? Yeah. It costs energy to do it, but you can do it.
How much does that compare to the energy you get back in the difference in your engine versus your oxygen?
Usually people don't do it, so I think it's not that good. Yeah, in fact, usually they're limited by the NO production. So you want to keep the temperature lower. If you made it higher oxygen concentration, you'll make the temperature higher and you get even more NO, unless you go all the way to having pure oxygen to get rid of the nitrogen. So some people try to do that. It's definitely a possibility.
Assuming you could use the excess energy.
Yeah. So people right now are usually thinking doing it for stationary sources, where you could have a lot of equipment to separate the oxygen and nitrogen. It wouldn't matter because it's not. But on a vehicle, it's kind of a challenge to figure out how to do it. All right. Does anybody have a suggestion? How can we run a stoichiometric fuel to oxygen ratio and still keep the temperature lower? So what was the first one?
Inject water.
Inject water. That's one idea.
EGR.
EGR, so exhaust gas. So the general idea is if you can add something else, so you have to keep the fuel in the air in a certain ratio, but can you add some more material to increase the heat capacity? Then the adiabatic flame temperature will be lower. You'll have the same enthalpy from the reaction, but you divide it by a bigger heat capacity, so then the delta T will be lower. So that's the main idea for cases where you're locked at stoichiometric, is to try to just add more heat capacity. And so people do all these things. Some people inject water. Some people in cars, almost always, they do exhaust gas recycle, where you take some of the exhaust gas, which has CO2 and steam, and you'll try to mix it back up with your fuel-air mixture to try to keep the temperature lower. All right. All right. So if you get into this nitrogen chemistry, the paper that you have to read first is this paper by Miller and Bowman. And they went through a lot of different reactions of nitrogen and nitrogen chemistry, reactions that could lead to NOx. And they came up with estimates and sometimes calculations of some of the reactions and some experimental data. It's a nice review article, and it has like discussion of where all these numbers come from. And they had a pathway like this that they worked out. And you can see it starts out by CH reacting with N2 to make HCN. And then a whole bunch of chemistry that eventually makes some more NO somewhere. I don't know where NO is. Here it is down there. So there's like a pathway that goes like this way to NO. And then they also even studied how you can try to get rid of NO by some other reactions later. And so if you do get into this field, you definitely have to read this paper first. So this is like the baseline understanding. There's another, actually, I should have the citation. There's another paper by, it's a chapter of a book by Anthony Dean, A.M. Dean, in a book by Gardiner that's all about these reactions and has like 100 of the reactions discussed in detail about what the rates are, what's known about them, what the products are, estimates, pressure dependence, all kinds of details about it. So this Miller and Bowman is like the first one to read. And then when you want to know about the specific reactions, Dean's chapter in Gardiner's book is the second one to read. this CH plus N2, the very first step in the Miller-Bowman mechanism, it was measured by several people, but they're measuring, really what they're measuring is the loss of CH. So CH is a radical, and you make some CH and you react it with N2. It's pretty easy to put N2 into your reactor. And then you can measure the rate with pseudo first order. And there's a lot of agreement about this, pretty good agreement between the experimental data. And so Balch made a recommendation of what the loss rate is. But notice that they wrote down that they didn't know what the products are. So it could be HCN plus N, it could be NCN plus H, maybe something else. I'm not sure what that is. All right, so that's what Balch is a committee. He's a person, but he was the head of the committee of UPAC that was evaluating all of the reaction rates. So that's what if you look in the committee's recommendation, that's what they said. But then in 2000, Muskaleva and Lin said, no, the products are different. Here's the potential energy surface. We calculated all the values, and we come in, where's the beginning of this? Here we go. CH plus N2 is here. You go over some barrier, you go through a bunch of valleys and over a bunch of hills, and they say you end up at NCN because they said there's some problem with this pathway, it doesn't work. And so instead it actually goes this way. And it makes NCN plus H. So they said that that's what the product should be. But that's completely different than Miller and Bowman. Miller and Bowman said the product should be HCN. This has a really big consequences for the subsequent chemistry. But that's what the theory said. So then in 2007, Vasudevan, I'm probably mispronouncing his name, did a shot tube experiment and was able to detect the NCN directly using a laser at this particular wavelength, and found that the branching ratio towards NCN is basically 1. They said the worst it could possibly be, at least 70% of the flux must be going to NCN. But they think the number is 1. And they have the rate coefficient and everything. So it turns out Lin's calculation was correct, and the Miller and Bowman was wrong. Now this is a big problem in this field because Miller and Bowman is like the Bible of what this reaction is supposed to be. But it turns out the very first reaction in the sequence is incorrect. It has the wrong product. So this caused a big uproar. So then people still didn't believe it. They said, well, you just set up your experiment to see NCN, but we think really in the flame it'll be different. But then they did laser spectroscopy inside the flame using like laser diagnostic methods similar to what you'd learned from Professor Dreisler down the hall. And they found, oh, yeah, actually there's a lot of NCN right there. Boom, big giant peak inside the flame. I guess he was right. It is NCN. Okay, so now it's known it's NCN. And then since then, so this is 2010, so the last 7 years, there's been a whole ton of papers people trying to figure out, oh, we have to redo all the mechanisms. It's all NCN instead. It must be doing something else. And so that's the status right now. And I haven't quite up to the story, but that's probably graduate students today are trying to like figure out what NCN reacts to make and what all the reactions are and the rate coefficients and everything. So this is a problem. If you want to get a mechanism that makes NOx, if you have a mechanism prior to 2010, most likely it does not make NCN. It says that the product is HCN, and therefore the mechanism is baloney. It may still predict some things correctly, because maybe some rates were tweaked in there to make it match actual experimental NO yields. So maybe it's okay for making predictions, but it's for the wrong reason. It's getting maybe the right answer for the wrong reason. So if you're in the right reason, unfortunately, you might not have a whole mechanism yet. Another important thing is this emissions control, right? We said that we were going to emit the NOx. In the United States, if you want to buy a diesel truck now, it will come with an emissions control system where they react to urea. Now, urea actually decomposes and makes ammonia at high temperature inside the catalyst. So you're actually reacting ammonia with the NO. And that gets back to an old invention by a guy named Lyon in 1975. He realized that if you have NO in a smokestack, if you add ammonia, the ammonia will actually react with the NO and partially burn and to make N2 as a product. So this is really nice. You get two poison gases, they react and they make an innocuous gas. This is the kind of emissions control system you want. And they found out there's a certain temperature range where this window reaction runs. You can change this by, if you add fuel, the temperatures change a little bit because there's some fuel reactions as well. And then actually later people figured out some catalysts. So you can run it catalytically and run at a slightly different temperature range. So depending on what temperature range your smokestack's at, you can decide how you want to run it, and they understand this pretty well. This is a commercialized technology. On big smokestacks, this is actually done by a lot of businesses as a way to keep the NO emissions within the limits. The government puts NO detectors across the top of all the big smokestacks, measures how much NO, and if you exceed your allowed amount of NO emissions, then you get fined a lot of money. And so the way they control it is with stuff like this. And now in the trucks, they're doing it too. I don't know how they, well, anyway, it's tricky because you have to keep these guys in like 1-to-1 ratio, ammonia to NO. So you have to have a good measurement of how much NO you have, so you know how much ammonia to inject. So in a big stationary facility, it's no trouble. But on a truck, it's like you have to be pretty clever. You have to have little sensors and stuff. So I think those systems must be very complicated on the trucks. But I don't know. But somehow they got to work. Yeah.
So do you do this in addition to lowering the adiabatic clean temperature, so you minimize the NO?
Yeah. So I think in the modern trucks in the U.S., they do a lot of exhaust gas recycle and other tricks to try to reduce the amount of NO that's coming out. And then they also do this to try to get rid of some more of the NO. And they must have a very complicated control system because as you change the way you operate the truck, you accelerate or decelerate, the amount of NO coming out is going to change a lot. The flow rates are coming out changing. And so there's I think quite a complicated whole system there to try to get under control. But the standard is very tight, so you have to do a lot of things in order to do it. I'm sure they don't do anything they don't have to do. So, yeah. And if you buy, I think Mercedes has it's called Blue Tech. Have you ever seen something called Blue Tech? I think it's all this emissions control system. Here's the reaction. The key reaction is the NH2 reacting with NO to make nitrogen plus water, but it has a competing reaction that makes this NNH, which might go on to actually go back to NO. And so the ratio between these two products is very important. And in fact, it was observed right at the beginning that they can't be 100% to N2 because some of the observations indicated you keep on making radicals. You're not just making stables. And so Miller and Bowman knew about that way back a long time ago. Here's a paper of 2001 about this. And people were studying this for quite a while. But the side channel that makes the NNH wasn't that well known. NNH is really hard to measure because it immediately falls apart to N2 plus H. But they figured out how to do it, and so several different groups tried to measure this over a quite broad temperature range, and also to measure the total rate over very well, because it's quite important for understanding the emission control system, so you can control the amount of NO emitted. And then following all this, people have developed fancy burner types to try to control the NO. So this thing is called a reburn design, and what they do is first have a combustion zone, then they they run like fuel rich, then they put fuel, maybe stoichiometric, probably fuel lean to begin with, then fuel rich because they add some more fuel, then finally some more air to have a diffusion flame at the end. And by now, you're using the exhaust gases from the earlier combustions as your source of heat capacity to make the final temperature in the diffusion flame small. And also, you've burned most of the fuel before you get to the diffusion flame, so that the enthalpy release is less. And so this turns out to be a really good design for getting low NOx. Of course, it's complicated to get all the flows right. You see how many different streams there are? And you have to have all these flows just right so that you get a stable burner, stable flame, and you keep the NOx under control just because you keep all the ratios right. And basically the idea is to avoid ever having a case where you're having a really stoichiometric mixture with no diluent burning, because otherwise the temperature would be too high and you make the thermal NO. It turns out in this system, they figured out that this particular reaction was like super crucial for calculating how much NO they had. So then a lot of people spent a lot of time measuring this one. All right, now let's talk about ignition chemistry. So there's two different types of ignition that you'll run into in combustion. One of them is induced ignition, where you force it by a spark or a laser pulse. And basically, you just blast some mixture that has some fuel and some air in it to some incredible temperature with a plasma, and it is definitely going to burn. Okay? And then the key from that is you start at a little volume of it burning, and does that little volume propagate and expand to make the whole thing burn, or does it blow out after it's burned? And I'm not going to talk about that problem at all. It's a very important problem, but I don't know much about it. And I'd say, in my opinion, that's mostly, a lot of that's about the combustion physics stuff that Professor Montalon's talking about. Is about if you have a little tiny flame ball, does it expand or not? If you have it under a turbulent flow, does the turbulence blow it out? Stuff like that. I'm going to talk to you about is the chemistry version. The chemistry version is called autoignition. It's where you just spontaneously combust something by mixing up a fuel and air mixture at some temperature. And if you're above a certain temperature, then it's called the ignition temperature, the flame's just going to ignite. Diesels are designed to use the autoignition. And usually you want the ignition delay to be very short in a diesel. Whereas Otto cycle engines, they don't want autoignition to happen, so you want the tau to be super long. Okay, so there's several different reasons. The spark-ignited engines are constrained by NOx, so anything you can do to improve this, to make the ignition delays longer, will help. The diesel engines, about 50% of the effect of how diesels work is controlled by this chemistry of the autoignition. There's another whole 50% that's sort of controlled by mixing and flows and stuff like that, which I don't know anything about. So I'm just going to talk about the chemistry part. If you really want to understand diesel, you have to understand them both because they really couple together. And then when you bring in alternative fuels, you have to worry about this a lot. And then there's a lot of interest in these things called LTC engine concepts, where you're trying to intentionally make the fuel burn at very low temperature so the emissions will be very low. And also you can make the fuel economy better because you have less heat losses if your peak temperature is lower. So there's a lot of concepts of trying to do that. And in those concepts, many of them rely on compression ignition, autoignition, to ignite it, because often you're at a condition where the flame speed is too low that if you lit it with a spark, it wouldn't actually propagate across the cylinder in time before the piston moves up and down. So you have to do volumetric combustion by autoignition. Because this is really important, this topic has been studied a ton, but it's still a problem. That's why I'm teaching it today. But if you want to know about it, you have to go back and read these reviews. And these review articles are really good. And PECS means Progress in Energy and Combustion Science. That's like the main review journal. For the kinetics part, Comprehensive Chemical Kinetics is the main review journal. And I'd say that there's a very detailed quantitative understanding of a couple simple fuels that really work, but a lot of problems at the low temperature part. And I'm just going to talk about what I think is interesting and important. And if you really should read these articles, and these are like hundreds of pages of text, so I'm sorry, there's a lot of material, but no. All right, so this is fundamentally what you got. These are ignition delay curves. And what these experiments are is you start the fuel air mixture at some temperature, you run it adiabatically, starting from that temperature. So it starts at that temperature, but then it heats up itself because it's reacting. And you measure it until you see a huge hot flame. The pressure goes way high, maybe if it's closed, or if you see emission from like everything because it's hot. And at the time when you see that emission, you say, okay, it's burned. And I'm measuring the time delay between the time that I jump the temperature up to whatever my initial temperature is, and then the time before I see the hot flame. And that time can vary over orders of magnitude. So this is from 1 millisecond up to like 10,000 milliseconds. Okay? So 4 orders of magnitude variation in this ignition delay. And this is one of the properties that's most sensitive to fuel. A little tiny change in the fuel can make a gigantic change in this ignition delay. At low temperature, these are pretty much straight lines of log versus 1 over t plot. And so this is like Arrhenius behavior. So you have like Arrhenius behavior at low temperature, and you also have Arrhenius behavior at high temperature. So at low temperature and high temperature, it looks kind of like normal chemistry. It's Arrhenius. In between, it's backwards. The ignition delay, you heat it up and you make it take longer to react, which is like totally against all rules of how things are supposed to be in the world. But that's the way it really is. So you have this thing called the negative temperature coefficient region, where the slope is backwards on these plots. And so if you want it to ignite sooner, you should actually cool it down, which is like really strange. But it's important to keep track of that this temperature is the initial temperature And all of these traces go through the entire range from the initial temperature all the way up to really high temperature when they burn. So they're actually, you're seeing time is the beginning point of a long time trajectory of all different temperatures. All right. Up at high temperatures, the small molecule chemistry explains everything. And you can run the models, it just works. If you want to, you can look into it and figure it's all about how the fuel breaks down to make H atoms. The H atoms do H plus O2. It's all pretty straightforward. And a lot of models can predict this correctly, and this is really well understood. Down at this low end, you can get a correlation that this effective EA is approximately the average of the EA for 2 different steps. And you can read about this in a paper 2015 by Merchant, where they figure out why that behaves that way. In between, I think we don't know yet what's going on. All right, the combustion chemistry, ignition chemistry changes dramatically with the temperature, the partial pressure of oxygen, and the pressure. At high temperatures, we talked about before, it's all H plus O2. H plus O2 makes the radicals, and then as soon as you attack the fuel, it immediately breaks apart and makes some H atoms. And this is basically the whole thing that's going on. And the chemistry is very fast, often faster than the mixing times. The unimolecular reactions of R are faster than anything else R can do. And so this is all relatively straightforward. As you go down to medium temperatures, the R radicals live long enough to react with oxygen. And mostly what they make as a product is mostly HO2. And then you get a lot of hydrogen peroxide from the HO2. And I'll show you this cycle. So this is a little bit more complicated. And the critical thing here is the sealing temperature for R radicals reacting with O2, this equilibrium. If you're above this sealing temperature, so you want to stay as R plus O2, you won't make RO2, instead you'll make HO2. And you'll be in this medium temperature regime. As you lower the temperature, eventually you get to the point where this equilibrium is on the right-hand side, and you'll make RO2, and that's different. And that's this chemistry here. R plus O2 goes to RO2, and then you get a lot of complicated chemistry of the RO2 that eventually leads to this species, and this species can break and make some more radicals, and that's your way you make your radicals. This, as you're originally running H plus O2, as you lower the temperature, this reaction, H plus O2 plus M goes to HO2, is killing off this reaction. It's stealing the H atoms away. And so that's why you get into this regime. All right, so the fuel starts at a low temperature and goes through all these different stages of the low temperature chemistry, then medium temperature chemistry, then high temperature chemistry, because the temperature's going up. And so you see the temperature comes along, and it gradually grows and grows, and then it does a funny little kink thing, and then it really goes zooming up, and that's the hot ignition. That's what you'd say was real ignition. And the fuel is like not doing much, and it's gradually getting consumed a little bit. There's a little kink here when the temperature kinks, and then all of a sudden, boom, it's all burned up in a millisecond or microsecond. In between, at low temperature, you make these kind of goofball peroxy species, stuff like this. Eventually, they go away, and you make hydrogen peroxide, you make formaldehyde. And then those things also vanish when you get to the hot ignition. It all burns up to CO2 and water. So this is the scale of what's happening. All right, so at high temperatures, pretty much well understood. And the issues here are all about complexity. So if you have a real complicated fuel, like a real diesel fuel or jet fuel, it's just you have a lot of species. But really, fundamentally, we understand it. So they're going to break down, and then the small molecules react the way we know, and H plus O2 dominates everything. And basically, we know it. And it's really, I think, it's no problem. It's just like getting your computer program to work better for the more complicated fuels. However, there is problems about soot. We'll come back to that later. Ignition is really about chemical amplification. It's about if you have one radical in, do you get more than one radical out? Once you get to that, you'll have fast reactions and explosions. If that doesn't happen, the chemistry will stop. If you get fewer than one radical out from one radical in, then any radicals you put in the system will disappear, and the chemistry will just stop. At least initially, when things aren't changing very fast, then you can say that the radicals, if you have positive feedback, will have an exponential growth. And then you can worry about what this eigenvalue is of the exponential growth. And that's a critical thing for setting the time scale for how fast the ignition will happen. So you can look in the Jacobian, look for positive values of the Jacobian of the right hand of the source term. And if you see a positive eigenvalue, you have positive feedback, and then you can work it out. Okay, let's do medium temperature. Medium temperature, what's critical to get positive feedback is this amplifier. And the way this works is that I have an HO2 radical. If it reacts with a fuel, I have two of them, say, then I react with two fuel molecules. I can make 2 moles of H2O2 and 2 moles of R. And then the R's will react with oxygen. The RO2 reaction reacts with R plus O2 goes to HO2 at these conditions. And so I had 2 HO2s to begin with. I made 2 radicals, and I got back to made 2 HO2s. So this part is not making any radicals. It's just cycling around. But I'm creating H2O2 as a product each time I go around. And the H2O2 thermally decomposes to make 2 OHs. And so these guys come, and now I have more radicals. So I have positive feedback. Every time I go in this green path, I get positive feedback. I get amplification of the number of radicals. However, these guys could also do this other path where the HO2s react to themselves. They make 1 H2O2, and then this has no positive feedback. So the blue cycle does not create any radicals. It just goes back around and around and around without making any radicals. But the green pathway does make radicals. So the green reaction here, HO2 plus RH, this is the critical reaction for chain branching for making radicals. So if you do a sensitivity analysis in your chemical mechanism, very often you'll see that the most sensitive reaction will be reactions like this, HO2 reacting with your fuel. It's not because this reaction is fast. This reaction is not fast. This is a very, very slow reaction. HO2 is a very unreactive radical. So this reaction is endothermic. It doesn't want to do it. But if it does do it, it's chain branching. It makes more radicals. So it's crucial. So this is the important reaction. And of course, this reaction is also endothermic. I take a stable molecule. I make two radicals. So I have 2 endothermic steps that both have to go to make the radicals. And so the EA for this process is pretty high. And this reaction is really very slow. So once you get in this regime, the whole chemistry is very slow. But there is a positive feedback. It's just really slow positive feedback. So you have a very low value of lambda, a very long tau, and you can get very long ignition delays. And in this regime, typically what you are is you're very sensitive to heat losses. If you don't have any heat losses, each time this thing runs, you make a little bit of heat, each time you do an oxidation, and gradually get warmer and warmer, and this thing will get faster and faster, and kaboom. But if you have heat losses happening, it's easy that they might be so big that they take away the heat, and they even make it cooler, and then this thing actually gets slower and slower. These endothermic reactions run slower and slower, and eventually it'll just fizzle out. It'll be a misfire. So you can have a misfire or explosion depending on exactly what the heat loss situation is during this very long time period that this slow chemistry takes to happen. This is understood moderately well. We think we know all the reactions. There's some quantitative questions. It turns out HO2 is unfortunately a really difficult species to measure. And actually, Professor Ju, he just told me this recently, they've made their first time-dependent measurement of the concentration of HO2. It's very hard to do. And this thing is usually happening in the middle. There's a low temperature chemistry, there's this middle temperature chemistry, and then you go to high temperature chemistry. The coupling at the two ends, as you're transitioning from low to medium or from medium to high, can be quite complex. So from a modeling point of view, it's a little bit complicated. It makes it hard to know. If you see a discrepancy, you're not sure what to blame. Is it because my low temperature model is bad? Is it because my medium temperature model is bad? Or is it because my high temperature model is bad? You're not sure which one, because you'll be sensitive to things at all the different steps. The last one is a low temperature chemistry. Well, let's see, I'll try to do this kind of quickly. So low temperature chemistry, people have worked out the main reactions, and this is the main sequence that makes radicals. So this is the chain branching, that if you get a radical, it makes an RO2, it isomerizes. The isomerized thing adds another O2. This thing isomerizes again. It makes a diperoxy thingy, which falls apart and gives a radical. This thing again falls apart and makes 2 more radicals. So you get 3 radicals out for 1 radical in. So that's your chain branching. But you can see this is kind of complicated, and we call these things R and Q because they can be all different kinds of structures. Each one of them has a different rates for every step. Many of these steps are reversible, so you have to worry about the thermo. And then there's a whole bunch of side reactions. The radicals can just fall apart. The radicals can react bimolecularly. They can fall apart a different way. This is what happens at medium temperature. This guy can also fall apart this way. This guy can do some different things, make water. It can go some other way. And some of these reactions are chain branching. Some of the reactions are chain propagating. Some of them are chain terminating. And they're all competing against each other at the same time. So this has been very confusing for the experimentalists to understand. And also, like until I think 2 years ago was the first observation of this. I think these guys have never been observed. So this is like these two species here. Some of these have been observed, I think. I think these have never been observed. So this is a lot of chemistry where no example of the key species has ever been observed. So this is where you have to trust the quantum chemists that they know what they're doing. And so that gives a lot of experimentalist heartburn. And we keep discovering new reactions. So three of these reactions on this plot were discovered within the last 5 years. Nobody had any idea. So I was involved in one of those. This pathway here, one of my students discovered. Nobody knew about it. So the one to water was discovered by people at Sandia. All right. This turns out to be very crucial, though, for the ignition delays at low temperature, which is very important for the knock. And this chemistry is really weird. It's a very strong radical amplifier, but it turns itself off because when the temperature goes high, some of the equilibria become run to the left. They don't run to the right anymore. So some of the reactions stop running. So it's like it runs, it makes a lot of radicals, and then it gets too hot, and it just stops. So that makes it a little confusing, too. And also, it's wildly sensitive to the molecular structure because each of those reactions has different thermo and different rates depending on the molecular structure of the fuel. So the teeniest tiny change in your molecule, of your fuel molecule, can drastically change this ignition. And definitely is not understood. Empirically, people had to work on this for a long time because they have to sell fuel, right? And they have to put a number on it. So they put this octane number on it. And then they made up this model called a blending octane model. And I would say basically it doesn't work. But they try. So if you do little perturbations of your fuel, you can get a little change in the octane number, make a prediction. Then recently, a lot of people do this thing called IQT-derived cetane number. Anybody do an IQT? I think some people in this group. Anybody? IQT? Yep. IQT? OK. So that's a gizmo you can buy. It's a way to measure an ignition delay. It's something like a diesel engine. So it gets numbers that are somehow correlated well with a diesel engine, so well that people use this actually to determine the cetane number, which is the rating of diesel fuels. But it's not really the diesel engine. And exactly why it's different, we don't really know. And it's kind of not a very fundamental test. Both these tests are just, they measure some time in some apparatus, but they don't explain to you why the different fuels do different things. And it's only in this very specific condition. And then the proxy chemistry is a big mess. We don't know the parameters that well. We don't know all the reactions. We're working on it. Some fuels show this two-stage ignition if you start with low temperature, where you see something happens in the temperature at a certain point, and then a little bit later, something else, the big explosion happens. And what that is this little kink in the temperature. The temperature goes long, and nothing's happening, and all of a sudden it gets a little bit warmer, and then nothing happens for a while, and then kaboom. And that's what you observe experimentally. If you measure like a pressure trace, you have a closed system, you can see the pressure goes up a little bit after a while, and then it doesn't do anything, and then all of a sudden it gets super high and explodes. And if you could measure the species like OH, you could see that they're exponentially rising at one exponential rate, and then later they rise, not quite exponentially, but still rise, and then they go down, and then they don't do much, and then they go up again. It's really weird. So this is like very complicated chemistry. But with the new spectroscopy methods, people can actually see this, and they can see the different rises and stuff like that. So you can see the OH going up and down and stuff, just like the models say it should do. All right, so the good news is there's clear stages. We understand this a little bit. And also only a relatively small number of species matter. I mean, it's pretty many, but it's maybe 20 or 30 species matter, not 10,000. And you can see the stages in the species profiles. You can see the rates, and you can write down the amplifier for how this is working as a cycle. And you can see fuel comes in, and you have some branching ratios, alpha, beta, gamma, that are telling you like how much of the radicals are staying in the cycle and how much are leaking out. That'll tell you how the gain changes. Let's take a break right now and maybe come back at 11:20.